Welcome to this session. This session, we are going to discuss about emission matrices. So let's start by defining what you mean by emission matrix. So a square matrix A whose elements are Ij is called emission matrix. If every Ij element of A is equal to complex or conjugate complex of complex conjugate Ij equal to the complex conjugates of the Ij element of A, i.e., we are saying that Aij is equals to the complex conjugate of Ji. And then, before we give example, a very powerful tool on emission, a necessary and sufficient condition for a matrix A to be emission is that A is equals to A power theta. Remember, A power theta was the transpose of A conjugate. I.e., conjugate transpose of A. So A equals to A conjugate transpose. So that is this necessary and sufficient condition for matrix to be emission. So let's give some, and then since for A to be emission, then Aij must always be the same as conjugate of Aj. Then consider the elements. Then let's consider the elements along the main diagonal of A, i.e., case when I equals to j. So that means we need to have ai equals to conjugate of ai. And this is only possible for an element to be the same as its conjugate. Then it means that that complex number must be purely real. So so for this condition to be satisfied, ai equals to the conjugate of ai, then we expect to have the complex number ai to be purely real. Just a minute. So we are saying that now we expect aii to be the same as conjugate of aii, means that this element if aii is the element a plus bi, then for ai which is equals to a plus bi to be equals to conjugate of aii, then aii must be purely real. So it's only a complex number which has only real parts that has the same value as its conjugate. So therefore, all the elements of the principal diagonal of a Emission matrix are real. So let's give some examples. of Emission matrices. So if we have 2, 3 plus 4i, then 3 minus 4i, and then 1. This is Hermitian matrix because all the elements along the main diagonal are real numbers, and A, I, J is the same as conjugate of A, J, I. B, if I have a matrix A, B minus ID, and then B plus ID, and then this is C, is also Hermitian because first case, elements along the main diagonal, all of them are real numbers, and of diagonal elements are conjugates of each other. Another example, C, is this matrix. So I'll have 1, 2 plus 3i, 3 plus I, and then 2 minus 3i, and then 2, and here we have 1 minus 2i. This is 3 minus I. This is 1 plus 2i, and then 5. This is also a Hermitian matrix because every element along the main diagonal is real number, and then every A, I, J is equivalent to conjugate of A, J, I. And in form of a question, if I have D given by A, and then say 6, 10, if this is 2i, and then this is 4 plus I, and this is 5 plus 6i, let's call this one X, Y, Z, then find X, Y, and Z for D to be Hermitian. Now, this is an interesting problem. It's simply testing whether you know how to define a Hermitian matrix or not. So remember, the first thing that already the main diagonal elements are real numbers, so that's okay. So remember, the condition is that Aij must always be the same as conjugate of Aji. So X is simply the conjugate of the element 5 plus 6i. So which will be 5 minus 6i. Well, this position and this position are the ones Aij, Ji. And then Y is the conjugate of this position here, 2i, which is the same as minus 2i. And Z is the conjugate of the element 4 plus I, which will be 4 minus I. Because you see, if you are to write this one in general form, then this position is A11, A12, A13, A21, A22, A23, A31, A32, A33. So X, which is A12, should be the same as conjugate of A21. So the conjugate of this one should give you this one value. So this is how we find X, Y, and Z. The next session will be discussing about skew emission matrices. Thank you.